Hello, my name is Eric and I'm with themoresuccessfulyou.com, and today I want to talk about the definition of the derivative. Alright, let's get into it. Okay, so in all modeling, in math, physics, in all different, in biology, in chemistry, everything, we want to be able to figure out how fast a certain something's moving. If we're talking about physics, we want to figure out how fast is the ball dropping to the ground, how fast is a car going into another car. In chemistry, it's how fast atoms are moving, and same with physics as well. Once you get into higher physics and in quantum physics, it's talking about how atoms move with each other. And so we need to have the concept of the derivative to be able to compute the instantaneous rate of change of an object. And so you can think about the derivative as essentially like the car's speedometer. So if we're going 40 miles an hour right now, then if f of x is the position we are on the earth, then our derivative will be 40. Our instantaneous rate of change of where we are on earth will be 40. So if we have a function f of x, then the derivative of f is equal to the instantaneous rate of change of f. Okay, so now let's draw a function. Let's look at what this looks like. Okay, so let's look at a point A. So I'll argue that the instantaneous rate of change is given by this line. That at this point, if we're looking, if we're right here, we're looking this way. We're looking straight out. And then as we turn here, then our instantaneous rate of change starts to curve up a little bit. Not so much curve, it just kind of goes up. And so now let's look at the definition of what this is actually telling us. So the definition of the derivative is the limit as x approaches a, f of x minus f of a over x minus a. That is the derivative of x. The derivative of x is given by f prime of x, given by dy dx, given by df dx. There's a lot of different ways. You can even go f sub x of x. And even if you wanted in multivariable calculus, people use this partial of f over x, but we'll get into that a lot later. So anyways, so let's look at what this equation's trying to show us, because I know there's always two parts to any calculus problem. There's the math and there's the picture. So let's look at this. So we were looking at the limit as f of x approaches f of a over x minus a. I'll draw one more picture. So here's x and here's a. So we want the derivative at a. And so f of x, so at this point, this equation is essentially the equation of it's the slope of this line right here. And as x starts going this way, this line looks like this. And then as we get a little bit closer, it starts to look more and more like that. And then once we get really close to A, it starts to look like our tangent line, like that. And the slope of the tangent line is the derivative of our function. Okay, so there it is. We have our definition of the derivative, and so let's take a step back here. So the derivative of a function is the instantaneous rate of change of that function. And so like I said, if we're driving in a car, then our speed will be the instantaneous rate of change of the car. So if we're on the highway and we're going 40 miles an hour, then that will be our derivative, our position's derivative on the map. And so if we're in our car and we're going 40 miles an hour, then we know that our position should be changing at 40 miles an hour, which is true. If it wasn't true, then physics would break. But so that's our example. It's the instantaneous rate of change of f. The equation that we solve is this to get our derivative. It's the limit definition, and there are shortcuts to compute this. We don't always need to compute the limit, as I'll go into in other videos. There's the power rule, the product rule, quotient rule. There's a lot of different rules that we can use to simplify this equation. And so, but it's very important to have an intuition behind this. And so, like I said, this gives us the slope of the tangent line at a point A, like this. So as x approaches A, then we get closer and closer to our tangent line, and the slope of the tangent line is the derivative of our function. So if you thought that this was of benefit for you, leave a like, leave a comment, and if you have any questions or you have any tips or anything that you want to talk to me about, please leave a comment and I will get back to you as soon as possible. Thank you very much and have a great day.